Okay, we're now going to discuss resistivity. Um, for a conductor, in the form of a uniform cylinder, so basically most wires are like this form because we assume the cross-sectional area remains constant. Um, we find that the resistance is proportional to the length. For example, if you double the length here, you're going to double the resistance. And we know that because if you were to make this length twice as long, you would have twice the voltage drop. And if you have twice the voltage drop, then that's going to affect the resistance and make it larger. Um, Also, if you make the wire itself or the cylinder larger in cross-sectional area, that will decrease the resistance. And you can think of this in terms of a water analogy. Imagine this was a pipe full of water, and if you were to make the pipe a larger diameter, then it would not restrict the water as much as it would be if it was a smaller pipe. So we're looking at a question number 3 here. We have a length of a wire, L, is given as 0.3 meters. The cross-sectional area is 8 times 10 to the power negative 5 meters squared, and it's producing a current of 2 amps. In question A, we're asked to find the resistance. And we learned in Ohm's law that the voltage equals the current times the resistance, or the resistance equals the voltage divided by the current. We're not given, oh, we are given the voltage here. I just see that voltage is 5 volts. So I guess we can get the resistance in part A using Ohm's law. So using Ohm's law, we have voltage equals current times resistance. So our resistance would be equal to V all over I. That's 5 volts divided by 2 amps, which gives us 2.5 ohms. So now moving on to part B, we're now going to use this resistance that we just determined to determine what the resistivity is. Now, the resistivity, I didn't discuss that. That resistivity is a constant, and that varies from material to material. If you go to your textbook on page 607, you'll find that there are different resistivities. It's very similar to, if you think of thermal conductivity, there's actually the resistivity is very similar to that idea. Some metals have different resistivities. Actually, if you look at your table, you'll notice, for example, that the resistivity of, for example, mercury is 95.8 and nichrome is 100, but then it's something like copper is 1.72, all to the power negative 8. So the larger the resistivity, the larger the resistance to that flow of current. So anyway, let's go ahead and calculate the resistivity. We're using R is equal to the resistivity times the length divided by the cross-sectional area. We rearrange this formula for the resistivity. This is basically the symbol rho, by the way, which is equal to R times A divided by the length. So let's now substitute our values in. We found out our resistance was 2.5 ohms. Our cross-sectional area was 8 times 10 to the power negative 5 meters squared. And we have a length of 0.3 meters. So go ahead and put that in your calculator, and you'll get a resistivity of 6.67 times 10 to the power of negative 4. And this is in ohm meters. If you look at this, the meters here will cancel with one of those meters, and you'll have ohm meters. And those are the units that we use for resistivity. Okay, and that's it for example number 3.